Okay, this example calculation is going to be a pressure vessel with a torque being applied to it. I've got a long, thin pressure vessel, which is 200 millimeters in diameter, with a wall thickness of 2 millimeters, so it's a relatively thin wall. And it's being subjected, in addition to the internal pressure of 700,000 pascals, it's also subjected to a torque of 5,000 Newton meters. We're going to have a stress element on the outside of this pressure vessel that has stresses in the X and the Y directions because of the internal pressure, but also shear in the XY direction because of this torque. Okay? So this is going to progress in 2 stages, since these clips have to be 10 minutes long or less in order to fit on YouTube. The first clip, I'm going to figure out normal and shear stresses. For the second clip, I'm going to show how to take those normal and shear stresses we've calculated and draw more circle so we can figure out the maximum normal and maximum shear stresses. So let's do first things first and figure out normal and shear stresses. First, let's write down the governing equations. Those are pretty simple. The Hoob stress, that is the stress that makes the pressure vessel want to grow in diameter, is pressure times the mean diameter, the average diameter, over twice the thickness. The longitudinal stress, that is the stress that's trying to make the pressure vessel grow that way, is half the Hoob stress, or that, over 4t. The last thing we need to know is an expression for shear stress due to this torque. And let's see, I'll write that over here. Shear stress tau equals torque times R over J, where R is the radius to the outside of the tube and J is a moment of inertia. All right, let's start with these two. Okay. The Hoob stress, remember the Hoob stress is the stress that makes the tube want to get bigger. Okay, it's in the radial direction, or the tangential direction. It makes you want to go that way. It's P dm over 2t. Well, let's see. Pressure is 700,000 pascals. That's in newtons per meter squared, times the mean diameter. The mean diameter is the average of the inside and the outside diameter. So the mean diameter is the outside diameter minus the thickness. Since we have an outside diameter of 200 millimeters and a thickness of 2, our mean diameter is 198 millimeters. I'm going to write that out in meters to keep the units consistent. And twice our thickness. There. Okay, I have a 2 millimeter thickness. Now let's check the units real quick. The stress should come out in pascals, newtons per meter squared. So if I cancel that and that out, I'm going to get pascals, right? This works out to be 34.65 megapascals. Now, to figure out longitudinal stress, we can either go through this calculation again, or we can do the shortcut. Since that's a 2 and that's a 4, the longitudinal stress is simply going to be half the Hoob stress, and that's what I'll use. So the longitudinal stress is 17.365, I think, 325 megapascals. All right, so I've got 2 of my values calculated. Last one's going to be that one. So let's clean up the board here a little bit. And let's see, how am I going to do this? And let's see, 34.65 and 325. Okay, so let's clean out some space here. There. Now, we need an expression for the shear stress in the tube due to the applied torque, due to a 5,000 Newton meter torque applied across the tube. And tau equals T R over J. T is given, we already know that in the problem. R is easy, that's half the diameter, so our R is 100 millimeters or 0.1 meter. Last thing we need to know is J. That's pi over 32 outer diameter to the 4th minus inner diameter to the 4th. Okay? J, if you want to think about it this way, is a stiffness. J describes the stiffness or the resistance to twisting, resistance to torsional deformation due to the shape, the cross-sectional shape of your tube. So the bigger J is, the harder it is to twist this tube. Now since this is pretty big, J is going to be large. Now J, if we figure it out in meters, is still going to be 10 to the minus something, okay? Let's put pi over 32, and this is going to be 0.2 meters to the fourth minus inside diameter, 196 meters to the fourth. And if I calculate that, that turns out to be 1.219 times 10 to the minus 5 meters to the fourth. My computer's about to shut down here, so let me, there. It's trying to restart for some reason or other. So there's J in terms of meters. Now a meter is really large, so J is really small when expressed in meters. If we were to express this in millimeters, we'd have to multiply this by 1,000 to the fourth power and get a very large number. All right. Using that for J, the shear stress, we calculate this out, with a torque of 5,000 Newton meters times 0.200 meters over this teeny tiny little number, but teeny tiny only because it's expressed in meters. It would be large if we expressed it in millimeters. And we get, make sure I get this right, 41.002 megapascals. So there you have it. We now have three stress components. We have a normal stress in the x direction due to longitudinal stress, a normal stress in the y direction due to hoop stress, and a stress due to torque that's a shear stress. So I have 1, 2, 3 components here. The next clip is going to be showing how to take these three components, that would be the x direction, y direction, and xy direction, and draw more circle using those.